Hello everyone, welcome to Enggclasses YouTube channel for a video lecture series in control systems. In this video lecture we shall consider sketch the BODE plot for the transfer function given and find the value of k for omega gc is equal to 5 radian per second. So now I need to solve this using the concept of BODE plot. Yes, let me consider the solution with this. So initially we'll have few steps. The first step is g of s. Step number 1, g of s must be in standard form. So now I can say that g of s is already in standard form. G of s is in standard time constant form. Standard time constant form. Time constant form. So what is that time constant form? Which is 1 plus t into s. So if I compare this with the equation, so in the denominator we have 1 plus 0.2 s and into another bracket 1 plus 0.02 s. So it is already there in the standard time constant form. The next thing is step number 2. I need to identify the different factors. So I need to identify the factors. Identify the different factors. So what is the first factor? The first factor is with respect to the gain. So what is gain? Gain k is unknown here. Gain k is unknown. So if k is known, we would have taken 20 log that value. So now as k is unknown and its effect is to shift the entire magnitude by, and its effect is to shift the magnitude plot by 20 log k. 20 log k in dB. What is the unit? It is decibel. So this is the first point. Now the second factor is number of zeros. How many zeros are there? If I look at the numerator, it is k into s square. S square means there are 2 zeros. So let me write the same thing. 2 zeros. 2 zeros at origin. 2 zeros at origin. This is very important. So as they are at the origin, so there must be a straight line of the slope. What must be the slope? That is also very important. A straight line of slope plus 40 dB per decade. So I would write plus 40 dB per decade. As it is there in the numerator, so it must be plus, and 40 dB, 20 dB is with respect to 1 0 and another 20 is with respect to another 0, and there are 2 zeros, so there must be a plus 40 dB per decade. So where it must pass, it passing through, so it has to passing through the intersection, passing through the intersection point of omega equal to 1 and 0 dB. Once we move on to BODE plot semi-log sheet, we would understand this. So till then let us consider this point. So now third one, moving further. So how many poles are there? So as I look in the denominator, there are 2 poles. So first let me consider the first simple pole. So what is the first simple pole we have? So which is known as 1 divided by 1 plus 0.2 s. So this needs to be compared with 1 divided by 1 plus t1 into s. So what must be t1 then? It is 0.2 second. So let me write t1 equal to 0.2 second. Therefore, omega C1 is equal to 1 divided by T1. So which is 1 divided by 0.2. So what I'm going to get? So I would get 5 radians per second. So I would get this as 5 radians per second. This is omega C1. Similarly, moving further, there is another what must this say? So there must be another straight line. So conclusion is, so a straight line with minus 20 dB per decade. Straight line with a slope, a slope of minus 20 dB per decade. So why minus 20? As it is there, as this pole is there in the denominator, hence it is minus 20 dB per decade for the value omega greater than 5 radians per second. So again, moving further, fourth point is there is another simple pole. So another simple pole. So what is that simple pole? Which is 1 divided by 1 plus 0.02 s. So what is this equal to? Again, comparing this with 1 divided by 1 plus T2 into s. So if I do the comparison now, I would get the value of T2. So what is T2? T2, I would get this as 0.02. So therefore omega C2 is equal to 1 divided by T2, which is equal to 1 divided by 0.02. So what that turns out to be? So it turns out to be 50 radians per second. So let me write this as 50 radians per second. So now I've got all these things. From this I can write the resultant slope table. So let me write this. From this resultant slope table, So first, starting slope. So where is the starting slope? Starting slope is at plus 40 dB. Starting slope is plus 40 dB per decade. Then for the omega value, omega greater than 0 and less than 5 radians per second, so it would still continue with the 40 dB per decade. It is an increasing slope. And then omega between 5 radians per second and omega greater than 5 radians second and less than 50 radians per second, it constitutes minus 20 dB. I mean minus 20 has to be subtracted from plus 40 dB. The resultant slope is 20 dB per decade. 20 dB per decade. And again, omega greater than 50 dB, greater than 50 radians per second plus or less than infinity. So this constitutes another minus 20 dB. So that 20 dB minus 20 dB would be cancelled. So I would get 0 dB per decade. So this is the ultimate slope table we have got over here. Is that fine? So just let me make this look a bit neat. Yes. This is what I have got now. So this is the resultant slope table. Once this is ready, so now I can consider the semi-log sheet and I can plot this onto the graph. So let me consider the graph over here. Yes, so this is the semi-log sheet. So what I have to do, so let me just divide these things with the x-axis indicates the omega and y-axis indicates the magnitude. So I would divide this x-axis as, so let me call, yes, let me call this as 0.1, and this is 1, and this would be 10 radian per second, and this would be 100, and this would be 1000, and so on. So this is omega. So what must be y-axis? Y must be in dB. So this must be in dB. Correct? So now I need to divide this. So here let me call this as 0 dB. From this moving up, so this would be plus 20 dB, and this I would take it as plus 40 dB, and this I would take it as plus 60 dB, and lastly it is plus 80 dB. It would go in this way, right? That means 1 unit is equal to 20 dB. Again in the negative axis, so what I do is this would be minus 20 dB, and this would be minus 40, right? Yes. So now initially what did I get? I get plus 40 dB. Just let me consider a straight line. I got a 40 dB. Where it should start? It should start from here at minus 40, and it would cross, yes, 0 at omega equal to 1 here, and it would move till omega is equal to 5. Where is 5? Here it is 5. Correct? Yes. Looks like almost done. Yes, this is the perfect one. So now, so this corresponds to 40 dB per decade. Before that, let me just draw one horizontal line starting from 0th axis. So here I would just draw a straight line, horizontal line. Yes. Yes, almost done. So now I would say from 5 to 50 there is 20 dB per decade. From this point, what I do is, from this point I would consider till which point? Till 50 dB per decade, till this point. Yes, almost done. Yes, here there is another 20 dB decade, and after that what would happen? There is 0 dB per decade. That means it would continue horizontally. Yes, the task is done. So what should I do now? So this slope, the initial slope which I got, I would call this as 40 dB per decade. So let me indicate that as 40 dB per decade. Once that is done, what is this slope? This slope I would call it as 20 dB per decade. So here I'm calling this as 20 dB per decade. And lastly, this is going to be 0 dB per decade. So once this is done, I can I have to identify this point. I would call it as A. Let me call it as A over here. So what is the height of this? So let me write this. So this is 20 dB plus 4 plus 4, that makes 28 dB. So this is useful for me while finding the value of A, that the value of K, that we shall see it later. So again we'll go back to considering the angle. So now let me go back here and consider finding the phase angle table. So let me write one more table here. For that, just let me consider phase angle. Let me consider phase angle table. So here I would consider the phase angle table. In the expression of g of s, I would replace s with j omega. So what would happen if I replace that? I would get g of s in place of s. I have g of j omega is equal to k s square. In place of s square, I have j omega square. This gets divided by, in the denominator, what do I have? I have 1 plus 0.2. Yes, in place of yes we have j omega, and again into bracket 1 plus 0.02. Yes, yes is again j omega. So this is the expression. For this I need to draw another table wherein the parameters are omega, and I have j omega square, which is there in the numerator, and there is another parameter, that is 1 plus 0.2 j omega, which is there in the denominator, and another parameter. For this, what I do is I'll just take its angle instead of taking this as 1 plus 0.2 j omega. So what I do is I would take its angle, which is minus tan inverse of 0.2 omega, right? So its angle is the term with respect to the term 1 plus 0.2 j omega. I would consider its angle as minus tan inverse 0.2 omega. So here for the second term it is minus tan inverse of 0.02 omega, and the last one is phi r, which is with respect to the resultant angle. So what is the value of value of omega? It takes 0.1 first, then 1, then it would take 10, then 100, and similarly it can go up to infinity, right? So just I need to fill up these table. So j omega square, it corresponds to plus 180 degree everywhere. So for all the values of omega, it corresponds to 180 degree, as it is there, as there are two zeros at 0. Yes, 180 degree. So now I need to substitute in place of omega as 0.1. It is minus tan inverse of 0.2 into 0.1. So I'll recommend you to make use of the calculator and fill this table and put it in a radians mode. So this is what I'm going to get if I make use of the calculator. Here I would get minus 63.43 degree, and here I would get minus 87.13 degree, and lastly I would get minus 90 degree over here. Similarly, I'm going to get minus 0.114, minus 1.145, minus 11.30, and similarly here minus 63.43, and lastly I would get minus 90. So what is the resultant angle phi r, which is the addition of all these things, 180 minus 1.145 minus 0.114. So if I do that, I'm going to get plus 178.74 degree, the first one, and similarly I would get the next one as 167.55 degree, the second one, and this is also plus, and third one is plus 105.29 degree, and then I have plus 29.46 degree, and lastly I would get 0 degree. So this table I would call it as phase angle table. Yes, this table I would call it as phase angle table. So this is also very important to get the phase angles. Once these angles are got, the next task is just to plot them onto the semi-log sheet again. So let me consider the semi-log sheet, go back here, and now I have to consider plotting these angles. So here again onto y-axis. So now I need to indicate what they correspond to, the angles I need to start with. So let me consider plus 180 degree over here. So every line corresponds to 30 degree. So here I would consider plus 150 degree. This one I would call it as 120 degree. This would be 90 degree, and similarly 60, 30, and the last one would be, this one would be 0 degree, correct? Yes. At point 1, at omega equal to point 1, I got nearly 180 degree, that is 178 point something, so I would get a point over here. So this is my first point, and second point at omega is equal to 1, I got it as nearly 167. So at here I would got it as 106. Yes, at omega is equal to 10, what is the angle? I got it as nearly 105 degree. So I need to plot that. Yes, at 10 this would be 105. So I would get a point somewhere over here, right? So this would be my third point. Similarly, moving further, at 100, omega equal to 100 radian per second, I got it as nearly 29 degree, 29.4846. So it is somewhere here, right? Yes, this is the next point. Now what I have to do is I just have to join these points to get the phase angle plot. Yes, I have to join this approximately. I cannot use the straight lines over here, so it has to be drawn freehandly. Yes, this I would call it as the phase angle plot. So this would continue like this. Yes, this is the resultant BODE plot which I have got from this. So only thing is I have not written the unit, so as I can write the unit over here to indicate what all they correspond to, right? Yes, so just let me indicate the y-axis. What I have in y-axis, 1 unit is equal to 20 dB, and there is another one angle with respect to angle, 1 unit is equal to, I would get 30 degree. So this is the graph. This is the scale of that, and once these are done, the next task is to calculate the values of k. So how would I calculate values of k? Let me come back over here and consider to calculate values of k. So let me write to calculate k. So what should I do? To get, it is said in the numerical, to get omega gc is equal to 5 radians per second. To get omega gc equal to 5 radians per second, the plot must intersect 0 dB. So I would say the plot must intersect 0 dB at omega equal to 5 radians per second. Omega is equal to 5 radians per second. But what is there at 5 radians per second? We already know that, but at omega is equal to 5 radians per second, point A is at 28 dB and it must be shifted down. So where was that? So if I go here and check, yes, this is the point. At 5 dB it is 5 radians per second. The point A is already at 28 dB per second, and it has to be shifted down to 0 dB, and this I would call it as A dash. So as it has to be shifted down, I would take it as a negative. So therefore at omega equal to 5 radians per second, point A must be shifted down. Point A must be shifted down. So I have to shift this point down. So what happens now? Therefore 20 log k is equal to minus 28. So therefore log k, I'm going to get this as minus 1.4, and ultimately what is the value of k? So if I make use of the calculator, I'm going to get this as k is equal to approximately 0.04. So this is the value of k. Yes, this is the numerical on the BODE plot. and I have explained this numerical very much step by step. I hope you people have understood. If there are still any doubts, please let me know them onto the comment section, and I'm happy to answer those doubts. Thank you so much for watching.